When you give a large language model a library of 50 or 100 tools and ask it to solve a complex multi-step task, it's not just picking one tool. It's solving a combinatorial search problem. It has to select the right subset from the library and determine the exact execution order. The standard approach across the field. Treat it like text generation. Use autoregressive decoding. But here's the catch. Autoregressive models suffer from a fundamental architectural flaw when dealing with combinatorial spaces. We call it early commitment. Once the model locks in its first few tool choices, it's mathematically constrained to follow that prefix. It can't look back and it can't revise. And no amount of temperature scaling, nucleus sampling, or beam search fixes it. Today, we're breaking down Diffusion-Guided, a new framework that completely sidesteps this bottleneck by decoupling tool selection from dependency prediction using diffusion guidance. Let's zoom in on why autoregressive decoding fails here. In standard next token prediction, every decision conditions on everything that came before it. In tool planning, that means the probability distribution over remaining tools becomes heavily biased by the initial selection. If the model picks a generic vision tool early on for a document understanding task, it effectively prunes the entire branch of the search space that requires specialized document analysis tools. This isn't a sampling issue. It's a path dependency baked into the sequential decoding mechanism itself. The authors validated this with a tightly controlled study. They built a synthetic task where the model had to predict a sparse subset of tools from a fixed 23-bit vector space. They matched model capacity, training data, and output length across all setups. The only variable was the decoding family. Under identical compute budgets, masked denoising raised PASAT-10 solution coverage from 0.320 to 0.943, compared to standard autoregressive sampling. Single candidate quality stayed roughly the same, but the diversity of valid hypotheses exploded. This proves that the limitation is intrinsic to sequential decoding, not a lack of randomness. Increasing the sampling budget just samples the same constrained trajectory more times. So how do you fix it? Diffusion-Plan, which stands for Diffusion-Guided Planning, introduces a propose refine select paradigm. It splits the tool graph planning problem into two distinct probabilistic stages. First, it uses a diffusion-based proposer to generate diverse candidate tool sets. Second, it uses a shared autoregressive refiner to predict dependency edges for each fixed tool set. Finally, it uses an inference time, judge-free value function to select the best candidate. Let's break down each stage. Stage 1 is the diffusion proposer. Instead of generating tools left to right, the proposer treats the tool set as a discrete sequence that gets iteratively refined. It starts with a fully masked input and applies stochastic denoising over multiple steps. Because diffusion models operate with global visibility, they can revise early decisions at any step. This completely breaks the prefix constraint. The model explores the combinatorial space in parallel, maintaining high hypothesis diversity. For the selection stage later, the proposer also tracks per-step token entropies. We discard the first few burn-in steps, average the entropy over the masked positions across the diffusion trajectory, and convert that into a confidence score between 0 and 1. This becomes a key feature for the selector. Stage 2 is the autoregressive refiner. Now that we have a fixed set of candidate tools, we don't need diffusion anymore. We need structure. Dependency prediction, figuring out which tool runs after which, is naturally sequential. So Diffusion-Plan passes each proposed tool set to a shared autoregressive refiner. Because the tool set is already fixed, the refiner doesn't have to solve the combinatorial search problem. It just predicts the directed edges that form the execution graph. This separation of concerns is critical. It lets diffusion handle the messy subset selection, while autoregressive decoding handles the precise sequential logic. Stage 3 is the judge-free value function. Generating multiple candidates is useless if you can't pick the right one. Oracle selection requires ground truth at inference, which isn't deployable. External LLM judges add cost and evaluation confounds. So the authors train a lightweight value function. It scores candidate graphs using only observable, deployable features. No Oracle access. The input to the value function concatenates several feature groups. The diffusion-derived confidence score, a structural heuristic combining validity and coverage metrics, predicted counts of tools and edges, a DAG validity flag computed via topological sorting, the candidate index to account for position bias, and multi-hot vectors over the predicted tool names and directed edges. The value function is trained via regression to predict a combined target that weights toolset accuracy and edge coverage. At inference, it simply picks the highest scoring graph. On TaskBench, Diffusion-Plan improves over autoregressive baselines by a 10% relative margin on tool F1. The gains are concentrated on complex compositional tasks like chain and DAG dependencies, where the combinatorial search space is largest. On API Bank, the proposed refine select interface transfers cleanly, proving cross-domain robustness. But does this just come from higher stochasticity? The authors ran systematic sweeps over autoregressive sampling parameters and compared against AR beam search. Even with top P set to 1.0, and even with beam search, autoregressive models couldn't match diffusion's proposal quality. The gains are strictly architectural. Candidate pool diagnostics tell the full story. With 10 candidates, the diffusion proposer raises union recall at 10 from 0.575 to 0.759, and union precision at 10 from 0.575 to 0.692. PassAtK measures aggregate coverage by computing the union recall against ground truth. A high value confirms the model has effectively explored the relevant search space. Oracle at K establishes the performance upper bound by selecting the optimal candidate via ground truth labels. The difference isolates the error source. Low PassAtK implies poor exploration, while a large gap to the upper bound indicates poor selection. With diffusion, the pool contains higher quality candidates, and the value function successfully recovers about 37% of the gap to Oracle performance. Error analysis reveals where the bottleneck still lies. Missing edges and missing tools are the most frequent failure modes. Interestingly, when you fix the tool sets to ground truth and only run the refiner, edge rec jumps significantly. That identifies edge refinement as the remaining bottleneck, not the proposal stage. Qualitatively, you see autoregressive models making semantically plausible but task-mismatched substitutions, like swapping document QA for image classification. Diffusion avoids this trap by maintaining broader coverage before committing to structure. DiGPlan demonstrates that treating tool graph planning as a pure text generation problem is fundamentally misaligned with the combinatorial nature of the task. By decoupling subset exploration from dependency prediction and replacing sequential prefix constraints with iterative diffusion refinement, we can unlock dramatically better candidate diversity without sacrificing structural precision. The inference time value function ensures this isn't just a research curiosity. It's deployable without external judges or Oracle labels. The code is already open source, and the proposed refine select interface is general enough to apply to other discrete planning and graph-structured reasoning tasks. If you're working on tool-augmented agents, multi-step planning, or discrete sequence modeling, this is a must-read. Check the paper and the repository in the description. Thanks for watching.